NENOMATICA, where mathematics meets YouTube excellence. In this example, we'll use symmetric expressions in the roots of a quadratic. First, we'll prove the identity for the sum of squares of two roots in terms of their sum and product. Then, we'll apply it to a specific quadratic equation to compute the value numerically. Step 1. Start with the algebraic identity. The sum of squares equals the square of the sum minus twice the product. We'll then replace the sum by capital S and the product by capital P. Step 2. Apply the identity to the quadratic 2x squared minus 5x plus 1 equals 0. By Vieta's relations, the sum of the roots equals negative b over a, and the product equals c over a. For it equals 2, b equals negative 5, and c equals 1, we get s equals 5 over 2 and p equals 1/2. Step 3. Substitute into the identity x1 squared plus x2 squared equals s squared minus 2p. Using s equals 5 over 2 and p equals 1/2 gives 25 over 4 minus 1, which simplifies to 21 over 4. As a quick check, we could also solve the quadratic to find the two roots and verify that the sum of their squares matches 21 over 4. This matches perfectly, so our identity and substitution are consistent. Final answer. The sum of the squares of the roots of the quadratic 2x squared minus 5x plus 1 equals 0 is 21 over 4. In this example, we will compute the sum of the cubes of the roots of a quadratic, using a symmetric expression that depends only on the sum and the product of the roots. Here is the problem. Example: solve 2x squared minus 5x plus 1 equals 0, and then find x sub 1 cubed plus x sub 2 cubed. Step 1. We use a symmetric identity for the sum of cubes of the two roots. The rule says x sub 1 cubed plus x sub 2 cubed equals s cubed minus 3ps, where s is the sum of the roots and p is their product. This comes directly from expanding open parenthesis x sub 1 plus x sub 2 close parenthesis cubed and subtracting 3 times x sub 1x sub 2 times the sum. Step 2. We compute the sum and product of the roots using Vieta's relationships. For ax squared plus bx plus c equals 0, the sum is negative b over a, and the product is c over a. Here it equals 2, b equals negative 5, and c equals 1, so s equals 5 over 2, and p equals 1 over 2. Step 3. Substitute the values of s and p into the symmetric rule and simplify. X sub 1 cubed plus x sub 2 cubed equals open parenthesis 5 over 2 close parenthesis cubed minus 3 times 1/2 times 5 over 2. That equals 125 over 8 minus 15 over 4. Converting to eighths gives 125 over 8 minus 30 over 8. And that equals 95 over 8. In this lesson, we will prove two beautiful symmetric identities that involve the roots of a quadratic. We will work step by step, keeping the algebra visual and intuitive. If a quadratic has real numbers x sub 1 and x sub 2 as its roots, then the sum of the roots is s, and the product of the roots is p. Equivalently, the quadratic can be written as x squared minus sx plus p equals 0. We will keep these definitions at the top of the screen. Our first goal is to compute x sub 1 to the power negative 2 plus x sub 2 to the power negative 2. We will show that it equals open parenthesis s squared minus 2p close parenthesis over p squared. Step 1. Replace negative powers by reciprocals. That is, 1 over x sub 1 squared plus 1 over x sub 2 squared. Step 2. Combine over a common denominator. The common denominator is x sub 1 squared times x sub 2 squared. Step 3. Translate the numerator and denominator using s and p. We know x sub 1 squared plus x sub 2 squared equals s squared minus 2p. And x sub 1 squared times x sub 2 squared equals open parenthesis x sub 1 x sub 2 close parenthesis squared. That is p squared. Applying those identities gives our result for the first goal. The sum equals open parenthesis s squared minus 2p close parenthesis over p squared. Now, for our second goal, we will evaluate x sub 1 to the power negative 3 plus x sub 2 to the power negative 3. We will show this equals s cubed minus 3ps all over p cubed. Step 1. Again, replace negative powers by reciprocals. That is 1 over x sub 1 cubed plus 1 over x sub 2 cubed. Step 2. combine over a common denominator again. The common denominator is x sub 1 cubed times x sub 2 cubed. Step 3. Express the numerator x sub 1 cubed plus x sub 2 cubed using s and p. Expand the cube of s equals x sub 1 plus x sub 2. S cubed equals x sub 1 cubed plus x sub 2 cubed plus 3 times x sub 1, x sub 2 times x sub 1 plus x sub 2. Therefore, x sub 1 cubed plus x sub 2 cubed equals s cubed minus 3ps. The denominator x sub 1 cubed times x sub 2 cubed equals p cubed. Putting the numerator and denominator together gives the result for the second goal. The sum is s cubed minus 3p s all over p cubed. A quick intuition. Notice that only the symmetric combinations s and p appear. Symmetric expressions in the roots of a quadratic. We will prove two identities step by step using clean algebra and Vieta relations. Here is what we want to show. First, the absolute value of x1 squared minus x2 squared equals the absolute value of square root of delta over the absolute value of a times s. Second, the absolute value of x1 cubed minus x2 cubed equals the absolute value of square root of delta over the absolute value of a times the quantity s squared minus p. Let ax squared plus bx plus c equals 0 have roots x1 and x2. By Vieta, s equals x1 plus x2 equals negative b over a, and p equals x1 times x2 equals c over a. The discriminant is delta equals b squared minus 4ac. From the quadratic formula, the absolute difference of the roots equals square root of delta over absolute value of a. Proof 1. Begin with the expression absolute value of x1 squared minus x2 squared. Use the difference of squares factorization to write it as absolute value of x1 minus x2 times x1 plus x2. Substitute absolute value of x1 minus x2 equals square root of delta over absolute a, and x1 plus x2 equals s. That completes the first identity. Proof 2. Start with the absolute value of x1 cubed minus x2 cubed. Apply the difference of cubes factorization. Absolute value of x1 minus x2 times x1 squared plus x1 x2 plus x2 squared. Rewrite x1 squared plus x2 squared as s squared minus 2p. Then the parenthesis becomes s squared minus 2p plus p, which simplifies to s squared minus p. Finally, substitute the absolute difference of the roots equals square root delta over absolute a. This yields the second identity. In this lesson, we will practice manipulating symmetric expressions in the roots of a quadratic. Here is our example. We will prove two identities using only the sum and the product of the roots. Let s be the sum of the roots and p be their product. Specifically, s equals x1 plus x2, and p equals x1 times x2. Step 1. We start from x1 to the fourth plus x2 to the fourth. View it as the sum of the squares of x1 squared and x2 squared. Apply the identity a squared plus b squared equals the square of a plus b minus 2ab. Now reduce each symmetric piece using s, and px1 squared plus x2 squared equals s squared minus 2p, and x1 squared times x2 squared equals p squared. This gives the first result. Step 2. For negative powers, we rewrite using reciprocals. x1 to the minus 4 plus x2 to the minus 4 equals 1 over x1 to the fourth plus 1 over x2 to the fourth. Put the terms over the common denominator x1 to the fourth times x2 to the fourth, which is p to the fourth. Use the result from step 1 for the numerator x1 to the fourth plus x2 to the fourth. That completes the second identity. Example. We will prove a symmetric identity involving the roots of a quadratic. Let ax squared plus bx plus c equal 0. Have roots x sub 1 and x sub 2. Define capital S equals x sub 1 plus x sub 2, capital P equals x sub 1 times x sub 2, and capital delta equals b squared minus 4ac. Our goal is to show the absolute value of x sub 1 to the fourth minus x sub 2 to the fourth equals the absolute value of square root of delta over absolute value of times s times the quantity s squared minus 2p. Before the algebra, a quick picture. Think of the two roots as points on a number line. The distance between them is the absolute value of x sub 1 minus x sub 2. That Distance will soon become the square root of delta over absolute value of a. Step 1. Use the factorization for the difference of fourth powers. A to the fourth minus b to the fourth equals a squared minus b squared times a squared plus b squared. Apply this to x sub 1 and x sub 2. Step 2. Factor the difference of squares. A squared minus b squared equals a minus b times a plus b. Then we get three factors: x sub 1 minus x sub 2, x sub 1 plus x sub 2, and x sub 1 squared plus x sub 2 squared. Step 3. Replace symmetric parts. We already set s equals x sub 1 plus x sub 2, and p equals x sub 1 times x sub 2. Also, x sub 1 squared plus x sub 2 squared equals s squared minus 2p. Substituting gives the absolute value of x sub 1 minus x sub 2 times s times the quantity s squared minus 2p. Step 4. Express the distance between the roots using the discriminate. Start with the identity. The absolute value of x sub 1 minus x sub 2 equals the square root of s squared minus 4p. Since s equals negative b over of s squared minus 4p. Since s equals negative b over a, and p equals c over a, s squared minus 4p equals b squared over a squared minus 4c over a, which is delta over a squared. Therefore, the absolute value of x sub 1 minus x sub 2 equals square root of delta divided by absolute value of a. Step 5. Substitute this result into the previous factorization. We obtain the absolute value of x sub 1 to the fourth minus x sub 2 to the fourth equals the absolute value of square root of delta over absolute value of a times s squared minus 2p. Proven. Recap. Factor the fourth powers, switch to symmetric sums s and p, relate the root gap to the discriminate, and substitute. This pattern works for many symmetric expressions in the roots. In this video, we will prove a beautiful symmetric identity involving the roots of a quadratic. Here is our goal. We want to show that the square root of x1 plus the square root of x2 equals the square root of capital S plus 2 times the square root of capital P. Here, S is the sum of the roots. S equals x1 plus x2, and P is their product. P equals x1 times x2. We assume x1 and x2 are non-negative, so that all square roots are defined. Before the algebra, here is an intuitive picture. Imagine a big square whose side length is the square root of x1 plus the square root of x2. Split that side into two pieces. A equals the square root of x1, and b equals the square root of x2. When we draw the cut lines, the big square is partitioned into four parts: a square of area x1, a square of area x2, and two rectangles, each of area a times b. So the total area is x1 plus x2 plus 2ab, which is x1 plus x2 plus 2 times the square root of x1, x2. That is s plus 2 times the square root of p. Now, let us present the clean algebraic proof, step by step, matching the structure. First, set capital A equal to the square root of x1 plus the square root of x2. Square both sides. Expand the square using a plus b quantity squared equals a squared plus 2ab plus b squared. Replace x1 plus x2 by s and x1 x2 by p. Because a is a sum of two non-negative square roots, a is non-negative, so we take the positive square root on both sides to get a equals the square root of s plus 2 times the square root of p. Finally, substitute back a equals the square root of x1 plus the square root of x2. This completes the proof. Recap. In this lesson, we will prove a beautiful symmetric identity involving the roots of a quadratic. Let x1 and x2 be real, non-negative numbers, typically the roots of a quadratic with sum s and product p. Our goal is to show the following identity exactly, step by step, matching the structure shown. Here is the statement we want to prove. Absolute value of the square root of x1 minus the square root of x2 equals the square root of s minus 2 times the square root of p. We will now follow the exact sequence of steps. First, define a to be the absolute value of the square root of x1 minus the square root of x2. Next, we square both sides. Then we expand the square. After that, we rewrite the sum x1 plus x2 as s, and the product x1 x2 as p. We then simplify to get a squared equals s minus 2 times the square root of p. Finally, since a is non-negative by definition, A equals the square root of s minus 2 times the square root of p, which completes the proof of the original identity. Summary. We defined A as the absolute difference of the square roots. Squaring and expanding produced x1 plus x2 minus 2 times the square root of their product. Recognizing s and p as the symmetric sum and product led directly to a squared equals s minus 2 times the square root of p. Taking the positive square root, since a is non-negative, completes the proof. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.